Section 9.3 discusses how the shape of the molecule impacts the polarity of that molecule. So before, just a little refresh, before we looked at if a bond was polar, right? So if I have X bonded with Y, we looked at the polarity within that bond. Did it have a dipole moment? We said that if the electronegativity difference between those two atoms was less than 0.4, this bond is called a nonpolar bond. If the electronegativity difference was between 0.4 and 1.8, we called this a polar bond. And if the electronegativity difference was greater than 1.8, we called it an ionic bond. So in this case, we're just talking about the bond between these two. Is like the Y atom pulling electrons more than the X, so much that the Y would have a partial negative and the X would have a partial positive. Quick correction, it's actually 1.7. Okay, so now when we talk about the molecule polarity, what we need to do is look at the bond between the atoms as well as the overall shape of the molecule. So if we have two bonded atoms that have a dipole, so they have that electronegativity difference greater than 0.4, then our bond is polar, which we just reviewed. But we now need to see if the shape of the molecule allows for those covalent polar bonds to either cancel out or not. So when we look at that, we have to look at both the atoms that are attached to the central atom, as well as if there are lone pairs on the central atom. So if we look at something like carbon dioxide here, we have carbon has an electronegativity value of 2.5 and oxygen 3.5. So there's definitely a big pull towards those oxygens. When we draw the Lewis structure for this and we look at the shape though, there are two electron domains with these two double bonds giving us a linear structure. And so we basically have two polar bonds that are being pulled in exactly the opposite directions, and so those end up having a net value of 0 for the whole molecule. So this linear molecule, since the pull is equal and opposite from that central atom, then the dipoles will cancel out, making this a nonpolar molecule. When we look at water, on the other hand, again, we have oxygen here bonded to two hydrogens. There's definitely a big electronegativity difference of 1.4, so it's definitely a polar bond. But here with water, we know we have two lone pairs on here, making this a tetrahedral molecule. And so we have the oxygens pulling up on those bonds, those electrons in the bond. So in a way, they cancel out in the horizontal direction, but there's nothing above the molecule, a bond anyway, to cancel out in the vertical direction. So we end up with a net positive pointing up for this molecule. So since there is still an overall dipole moment, we're going to see a part of the molecule that's very electron dense, so this part's very negative, and then one that's very electron deficient, so partially positive, making this molecule polar. Now it's easy to see when we have like only in 2 dimensions, it's easy to see, but when you get into 3 dimensions, it makes it kind of tricky. And so I want to teach you just kind of a general rule of thumb to think about that will make it a little bit more straightforward. But there are some like nuances within it, so I do want you to practice and keep this in mind. Basically, if we have a symmetric molecule, then we're going to have something that's nonpolar. So in all directions, meaning same atoms pulling from the central atom. But if we have an asymmetric molecule, so such as in water, we're going to get a polar molecule because those dipoles don't cancel out, leading to a net dipole. So here is my big rule of thumb that would lead you to a nonpolar molecule. So this is kind of like your checklist you can see if it's nonpolar. So if it's nonpolar, again, we need some symmetry. So meaning, you need to ask yourself, is the molecule, are all of the terminal atoms the same? If they are, then you know, like for example, for carbon dioxide, that the dipoles are going to cancel themselves out because the pole, the length of that vector here, or of that arrow, that pole is going to be similar on the other terminal atoms. But that's not it. We also have to consider, because with water we have both terminal atoms, right? Both of them are hydrogen, so why is it not? We also have to consider, are there any lone pairs? If we want it to be nonpolar, there should be no lone pairs on the central atom. So if you ask yourself, if you say, ask these questions, are all the terminal atoms the same? And you say, yes, they are. And you say, are there no lone pairs on the central atoms? And you say, nope, there's no lone pairs on the central atoms. Then your molecule is most likely is nonpolar. Period. It always is nonpolar. There are a couple cases where you might have a lone pair on the central atom that would make it still a nonpolar molecule, as well as you might have some terminal atoms that aren't the same. That would only be the case if they have the same electronegativity value, but that's very uncommon. So this will always give you a nonpolar molecule if you can check off those boxes. But I'm going to give real quick into the caveats of this. The two cases where you do have some lone pairs on the central atom and it is nonpolar. And this, again, just has to go back to symmetry. Okay, symmetry is key here. So if we look at if you go back to the table that has like all of the different shapes on it, then you can see that there are two that look pretty symmetric on their own. And that would be when we have trigonal bipyramidal geometry where it has three lone pairs. This gives us the linear shape for the molecular geometry. So when the electronic geometry is trigonal bipyramidal and the molecular geometry is linear, and those two terminal atoms are the same, then this is also nonpolar. And then one more, other one, where there's lone pairs is when we have octahedral electron geometry and two lone pairs. If all of the terminal atoms are the same, then for the molecular geometry of square planar, then we would have something that's nonpolar. So let me just draw it. If we looked up from the top, we have central atom in the middle, we have terminal, 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 and we have two lone pairs. Those lone pairs are coming from above and below the way I've drawn it. And so the dipole, let's just say that the terminal atoms have a dipole moment towards them, then those would all cancel out. So we would have these two dipoles canceling out there, and these two dipoles canceling out in that direction, leading to a nonpolar. So these are my only caveats, molecular geometry of linear and square planar, where we have a nonpolar molecules when we have some lone pairs. All right, so for this one, we need to go back to our last practice problem. So I want you to scooch back. I also just put them here. And because we need to see the Lewis structure and look at the shape to consider if it is polar or nonpolar. So if you remember for ozone, it was trigonoplanar bent. And so if we think about those considerations, I'm going to put that up here. Remember, the considerations are, maybe I'll put it to the side. We need to ask ourselves, so it'll be nonpolar if their terminal atoms are the same, and no lone pairs on central atom. If you can't check off both of those boxes, it's going to be polar. So if we look over here at ozone, the two terminal atoms are the same, so that checks off that box. The oxygen atoms are the same, but there is a lone pair. So this actually does make this a polar molecule because of those lone pairs. Let's look at tin trichloride, complex ion. It has all of the terminal atoms are the same, but it does have a lone pair as well. So in this case, we also have a polar molecule. And that's just due to the fact that this is trigonal pyramidal, and so we have a lone pair in the up direction where that would cancel out for tetrahedral, and so this one is asymmetric. Looking at selenium dichloride, we have the two terminal atoms, chlorine, are the same, but we have two lone pairs, so this is actually similar to water. This is tetrahedral bent, so it is also polar. Now for carbonate ion, there again we look at the terminal atoms. They are all the same. There are no lone pairs on our carbon atom, so we can say that this ion is nonpolar. Okay, similarly over here for these last four, if we look at them, we have 4 fluorines attached, cool, but 1 lone pair, that makes that polar. We have all fluorines here, so that's good, but there's a lone pair, so this one's polar. Here we have 4 bonds towards chlorine, 2 lone pairs. Now, if you remember, this is why the shape matters, because these 2 lone pairs, this is octahedral, 6 electron domains. It's octahedral, but the 2 lone pairs are above and below, so this is a kind of a bird's eye view, so this one is actually a nonpolar molecule. Square planar, if the atoms are the same, it will be nonpolar. And then this last one, bromine trifluoride, we have 4 fluorines, no other atoms, so that's good. 2 lone pairs, this is actually a T-shaped molecule, it kind of looks like this, and so there's nothing over on this side of the molecule to cancel out that fluorine on top, so this is a polar molecule. The last thing we're going to do in this section is looking at larger molecules. In most cases, you're going to have more than one central atom. So to be a central atom, you need to have 2 or more atoms attached to you. If you are a terminal atom, you're just attached to 1 atom. So if a molecule has more than 1 central atom, you actually have to look at the geometry around each of those central atoms rather than looking at the molecule as a whole. I will say most larger molecules are going to have, are more likely to be polar just because of more arrangements, less likely to be symmetric. Although I will say, anytime you see a molecule that has lots of carbons with hydrogens like this, so carbon, hydrogen, hydrogen, carbon, hydrogen, hydrogen, this is a notation of a nonpolar molecule, or a nonpolar section anyway. These carbon-hydrogen bonds are very nonpolar, and when you have a long chain of them, this brings a nonpolar region. This is called like a hydrophobic region of a molecule. So in some cases, you can have really long molecules that are nonpolar, but if there's oxygens with lone pairs or nitrogens with lone pairs, then it's going to get a little bit more likely that it's polar. But regardless, you do have to look at the geometry of each central atom rather than that molecule as a whole. So here we can see in this molecule we have a central atom on this carbon on the left, the carbon in the middle, and the oxygen on the right is bonded to 2 other atoms. So we have 3 central atoms here. If we look at this first central atom, we can count the number of domains. We have 1, 2, 3, 4 bonds, no lone pairs, and so this would be tetrahedral geometry. and also no lone pairs, so the molecular is also tetrahedral. Here for this center carbon, we have one atom towards another carbon, one to the oxygen, and a double bond over here to another oxygen. So 3 domains, making this trigonoplanar, and molecular is also trigonoplanar. Now, if we look over at our one on the right, we have an oxygen. Now, what's not written, because this is the shape, is the oxygen is missing it's not written, the 2 lone pairs, right? This is tetrahedral bent. And so, yeah, sometimes we won't see those lone pairs if it's not a Lewis structure, so you want to keep that in mind. Look at the shape, right? It's not linear, so there's something bending that bond. So those are the lone pairs. So now we're going to look at how a large molecule such as this, or a larger molecule, we could look at these, predict the bond angles in vinyl alcohol. So this is vinyl alcohol, and we're going to predict the bond angle. So first one we're going to do is between the carbon, or the hydrogen, oxygen, carbon. So that is this bond here, bond angle here, and then between the oxygen, carbon, carbon, which is this one here. So we have 2 different bond angles we're going to look at. So we want to look at the central atoms in both cases. So for this first one, we're looking at this is the central atom. We can see that oxygen is bonded to 2 atoms and 2 lone pairs, so 4 electron domains, 4 domains, 2 bonds, 2 lone pairs, and that means we are tetrahedral. Anytime we have tetrahedral, it's going to be 109.5 degrees for that bond angle, but we know there are some lone pairs on there, so we're going to make that less than. All right, and then in this next case here, carbon is our central atom, bridging those the oxygen and the other carbon. So we're going to count those domains. We have, let's do green here, we have 1, 2, 3 on this carbon central atom. So 3 domains. They are all bonds, 3 bonds, no lone pairs. And so this is trigonoplanar. And we're looking at the bond between those. So you could definitely say 120, but keep in mind there is that double bond there, which is going to take up a little more room, and so it's actually going to make this bond angle a little bigger and then squish these 2 together. So this one we would actually say is a little bit greater than 120. But again, those are a little bit more into the specifics and details. As long as you are getting that it's about 120, you are good.